All right, hello and welcome everybody to the Illinois EPA Office of Energy's Public Water Infrastructure Energy Assessment Program webinar series. We're so glad to have you here today. Thanks for everybody to saying hi in the chat. It's great to see everyone on today's call for our webinar, Control Strategies for Aeration Equipment for Activated Sludge Plants. This is the last of our three-part series in aeration and energy. And of course, the most important one, control system. So we're thankful to have you here today. In this session today, we'll present a variety of aeration control technologies, and we'll also talk about how to best tune your equipment processes or to your process needs. We'll dig into a lot of different pieces about key aspects of control strategies for your equipment, and we have some amazing speakers here that are going to share their best strategies and knowledge with you all today. We have Shawn Maurer, who's a senior energy engineer at SEDAC here that will be joining us and speaking here shortly. We have Zia Qureshi. He is a subject matter expert from NORESCO. And then we have Jonathan Grabowy he's the managing civil engineer at the Metropolitan Water Reclamation District of Greater Chicago. So we have a very stacked webinar today. We're very excited to have you all here. As a reminder, please feel free to use the chat or the Q&A box at the top if you have questions throughout today's session or comments. Just let us know what you think. But we will have a Q&A session at the end of today's webinar. Also, feel free to also change the settings in your Zoom. You can do different visuals and views. If you go to the top right corner of your screen, you can look at more and you can have different views of today's session. Finally, the all-important CEUs and certificates. So we will provide the CEU course number and certificates to all participants on today's webinar session. We're still waiting for the course number from Illinois EPA, but as you know, we will get that to you as soon as it is available. So hang tight. You don't have to request a CEU or certificate. I'm going to send it to everybody who attends today. So I will get you that CEU course number and participation certificate as soon as we possibly can. Finally, just to let you know, we are recording today's session, so we will provide all the slide decks and the recording of today's session probably later today or tomorrow to everybody who attends. So thank you once again for being here today, and we're excited to have you. So before we go into the contents of our presentation, just a reminder, so I'm with the Smart Energy Design Assistance Center, and at SEDAC, we help communities reduce the footprint, their energy footprint. And did you know wastewater systems are one of the biggest energy users in municipalities across Illinois? So through our work with the Illinois EPA Office of Energy, we provide no-cost energy assessments to wastewater and water treatment plants throughout Illinois. We also provide no-cost technical assistance. So if you're doing an energy efficiency project or work at your facility or exploring the opportunities to do that, we're here to help. Our comprehensive energy assessment reports list the cost of upgrades, estimated payback period. We provide recommendations or energy cost reduction measures for your plant. And we also look at applicable incentives or funding opportunities for you. So it's a really great way to identify energy savings for your facility. And you know, whether you have a new facility or an older facility, it's a great opportunity to uncover some opportunities to save energy and money. We also, as a part of this program, offer these continuing education events. So we're really thrilled to be able to do this work in with the Illinois EPA. And you know, we talk a lot about why you should complete an energy assessment. So if you have an older existing system or you haven't had an assessment before, it can identify missed opportunities. You can plan for upcoming capital improvements and see what incentives and funding are available to support those initiatives. You can also get that third-party support for ideas at your plants. And that's one of the things that a lot of our operators and wastewater teams that get assessments really like, is they're able to provide the report to their city council or leadership to help make decisions and push energy efficiency projects forward. So it's a great opportunity to identify what's possible, but also identify support to be able to actually move those projects forward. And if you have a new or recently upgraded plant, it's always good to see if it's operating at its peak and most efficiently. So there's always room for more improvement. If we come out and do an assessment, we don't find anything, we'll give you a thumbs up, and that's a great thing to share with your team and your municipality. But really, we can also help if your plant is new or recently upgraded, plan for those future projects, and look at new technologies and processes that might be out there. So new plant, old plant, an energy assessment is always a good idea, and there's always opportunities to find incentives and funding for the work that you're looking to do at your facility. So if you're interested in an assessment, feel free to either send me an email or pop interest in the chat or the Q&A box, but you can also apply at sedac.org/water. And the qualification, you have to be located in Illinois. You have to be willing to allow us to come on site and actually do a walkthrough of the facility, and be willing to share facility information like utility data, operating DMRs, your process flow diagram. So helping us get to know your plant a little bit more, and also share the final assessment report with Illinois EPA. Now that assessment report only goes to the Office of Energy, it does not go to regulatory bodies. So we're really just interested in helping you save energy and money. Data collections is the next step. And so I'll schedule a 30-minute call with you usually to get to know your facility a little bit more, and then collect information from you. This is the meat of your role in the assessment process, is helping us provide those 2 years of utility bills and your DMRs. And then we're here to help you or we're here to assist you in getting that information, so we can work with your city clerk or someone who manages the bills to get that information. But once you provide the key data that we need to do our assessment and help walk us around on site, we'll handle the rest. So we actually created that comprehensive report for you. We come out and do a site assessment, and then that report can be a great tool to implement energy efficiency opportunities for your facility. So if you're curious, I'd love to learn more about your plant, and just let me know if you're interested in an assessment, and we can explore whether it might be a good fit for you. So today's webinar will actually be is one of 3 different, we're doing a series for both activated sludge and lagoon systems. And all of these prior webinars can be viewed on our website. So please feel free to access those webinars, the videos, if you're curious about our past sessions or haven't attended. I know a lot of you have, though. And now, thanks for listening a little bit more about our energy assessment work. I am going to pass it over to my colleague, Shawn Maurer, to take it from here. So thanks, Shawn, for presenting today.
Thank you, Cassie, for the introduction. As Cassie mentioned, I am a co-worker at the Smart Energy Design Assistance Center. I have a mechanical engineering background, and I've been working with SEDAC for a total of almost 6 years now. The wastewater and water assessments have been a big part of the program since the beginning. We've been doing a lot of this work under DCEO back in the DCEO days for our program. Now we're working directly with utilities for incentive programs and with the EPA Energy Office. So just to kind of review what we've done previously with our presentation sequences, we started off covering aeration and energy for activated sludge and lagoons. So we were looking at VFD control of blowers, kind of optimizing that connection between the diffuser system and the blowers. And then we looked at actual efficiency of the diffuser systems, mechanical mixing systems, how to actually get the oxygen into the water in the second part of our series. So now we're going to actually look at control systems. We're going to dig a bit into how the SCADA interacts with those aeration systems, and how to look at those for optimizing system control. Next slide, please. So just to review our first presentations, when we were going over aeration efficiency, we touched on oxygen transfer and transfer rates, the different aeration methods as far as surface aeration devices, membranes, diffused aeration on the bed of a basin, sensing those levels through different types of sensors, controlling the blowers through time clocks, VFDs, manual versus automated processes. We're going to dig a little bit more into that control in this presentation. And then we looked at blower efficiency as far as the blower system, using positive displacement versus centrifugal, keeping an eye on your turn down ratio so you can optimize efficiency when you're at less than design load. Next slide, please. The next part of our series was covering the actual efficiency of the diffuser system. So again, we went over oxygen transfer in a little more depth detail. We touched on alpha factors and how that impacts the efficiency of aeration technologies. We got in a little more detail on surface versus diffused aeration systems. And then we looked a little bit at the connecting piping and stuff, the leakage that you can have there, maintaining those systems to optimize the energy input for aeration. And so now we're going to dig into the actual control strategies. So just some control basics. There's two main categories of control. There's manual control, which is pretty good for small plants. It's usually not as cost effective for them to go fully automated if it's a small plant. Tend to see on-off control or manual adjustment on a seasonal basis of VFDs if they're installed. But for larger facilities, manual control gets difficult to do. You've got a lot of complex interacting systems. And so you tend to rely more on automated control where you've got sensors in your basins that adjust airflow, cycling rates, return flow rates for sludge, things like that. And that's what the bulk of what we're going to be covering in this presentation. Next slide, please. Basic things to know are the variables that you're controlling, how the control system is going to interact. So you're going to have a control variable. Most people are familiar with DO is usually a control variable for a lot of activated sludge systems. We'll dig into more details on different control variables here in a minute. Then you'll have a set point reference variable. So this is your DO setting in your SCADA system that you're trying to target. Or it could be an ammonia setting, could be a flow rate target, depending on your control system. The next part of that is the controller. It's going to have the logic contained in it that's going to dictate how the system responds to changes in your control variable from the set point. And then there's the disturbance. That's whatever's coming into the plant that's driving your system away from that set point. So moving on to our control concepts. What we see at a lot of plants currently is a reactive or feedback control strategy. You've got a DO sensor in a basin that's measuring DO, and in reaction to that, you adjust the speed of blowers, the positioning of valves, in order to maintain the set point of the DO system. It's a very common strategy. It's been effective for a while now, but what we're finding with more advanced technologies coming out is we can now move into a predictive or a feed-forward control system. Usually this involves measuring a process variable ahead of what's coming into the plant, so you're measuring the influent, and you're trying to adjust ahead of time for those upsets in your process to provide a bit more stability than you get with a feedback system, where you have to have a disturbance first before you can react to what's going on. So this gives a little bit more stability in the process, better control, and it's a growing application for high efficiency systems. So we want to touch on that today. And just some basic schematics so you can understand kind of visually how these systems are working. On the left side here, we've got a feedback process. Your process variable has some disturbance come into it from your influent. The sensor picks that up, feeds that back into the controller for the system as an error deviation from your set point, and then your system reacts to that. The feed forward process, you've got a disturbance that's going into a sensor. Usually there's some kind of advanced logic in there, either artificial intelligence, some kind of modeling program that will adjust your system's settings and controls in order to maintain your controlled variable in a stable state. So let's just quickly go through feedback control. The simplest option is on-off control of blower systems. We see this sometimes in sequencing batch reactors, probably the most advanced system that does on-off control as you cycle through the different sequences of aeration, reaction, decanting, filling. But we also see this for lagoon systems and kind of the simpler activated sludge plants. We may see on-off control of the aeration basins. It's inexpensive, can be easily retrofitted into existing facilities that don't have SCADA systems set up already. It's pretty good control for mechanical aeration systems, or where you've got a blower set up on a per basin basis, where each basin can have a blower that reacts to its changes in settings. But it's a little more difficult to accurately control if you got a single blower feeding multiple basins, multiple different systems. A lot of plants with activated sludge will see a blower that's serving your activated sludge basins and also an anaerobic digester, possibly. And you can't really do on-off control with an automated system with those. You need a little bit more advanced control than that. It's ideally, you see this control for fully mixed reactors with long hydraulic and solids retention times. And you can improve this control with some additional sensors and programming. As far as on-off control, you can target with ammonia sensors or nitrate sensors. You can target denitrification and nitrification for those systems. But again, it's a fairly simple system. Usually we see this most often at plants that are doing a conversion from some kind of manual control and upgrading to a SCADA control. What we most commonly see, though, is a PID loop. So just targeting what most people are going to be familiar with is DO control of a basin. You've got direct adjustment of the air supply rate based on DO measurement in the basin. As you drift away from set point, you're going to increase or decrease airflow to get back to that set point. Again, this kind of control, if you're controlling multiple basins, you can have valves for airflow to those different basins that can then adjust individual basins to the desired airflow rate as needed. An advanced way to do this that we're starting to see is ammonium-based aeration control. So instead of putting a DO sensor in the basin, you've got an ammonium sensor or nitrate sensor in the basin. And a lot of plants are moving towards this because of the increased permit regulations for nitrogen limits in the effluent. The problem with direct feedback control with ammonium is it does have a slower response rate than DO, which can lead to more overshoots and wasted energy. It's generally more successful with on-off aeration control if you're doing a direct feedback control with ammonium. But usually what we see is it's paired with a DO sensor in a cascade control. You're going to measure the ammonia as you get a differentiation from your set point. That's going to send a signal to your DO controller. The DO controller sets adjustable limits based on what the ammonium controller is requiring. That DO controller then controls the aeration system speed to maintain within those set points. This prevents the overshoots that you tend to see with direct ammonia control without a DO backup system. So you get more stable control. And again, the target here is better decreasing your nitrogen effluent, meeting those tighter regulation limits. What we're starting to see now in marketing and things is feed forward controls, advanced controls using modeling programs, predictive logic, and artificial intelligence, which Zia will touch a bit more on in detail in his presentation. But just as a basic overview, one of the things, again, is ammonia-based control. You've got an ammonia sensor sensing things coming into the plant that's adjusting set points for a DO sensor in your basins. But the actual DO isn't being measured. There's a model that's adjusting those set points depending on what's measured in your influent water coming in. The model has to be accurate for proper function, otherwise you can get wide swings in your aeration set points and unstable function. And so what we tend to see is with this kind of basic feed forward ammonia control, it works best for plants that have a consistent influent coming in. They don't have wide swings in loading rates or things like if you have maybe large swings in I&I, or if you have an industrial client that may dump in slugs into the system. Usually what we see, as with the feedback control for ammonium, is this gets paired with a DO sensor in order to limit those swings. So you have kind of a combination of feed forward control for the ammonia sensor that's providing more rapid response for your facility. And then your DO is providing feedback to the system to keep you from swinging and hunting with your trying to hit those target set points. And so this is just showing a bit of a diagram of what that looks like as far as your control system. That feed forward again is providing that early warning of a process upset coming in by measuring what's coming into the plant before it actually gets into your process flow. So that's providing adjustments to your aeration as that influent is coming in instead of reacting to it. And so that gives you tighter control over the aeration system, gives you a higher quality effluent coming out of that process. Digging into a bit more of how that kind of AI system works, artificial intelligence software uses that real-time operational data compared to historic data in your plant. It's one method of using AI. So if you have good SCADA trends for your plant in historical data, a programmer will use that to build out a model, and your AI logic will then look at that as kind of a digital twin of your plant. So you've got historical data that shows how your plant has reacted in the past to different upsets coming into the system. So it has a history of how the system works. Then you've got a model next to that of optimized control, how it should work based on model data, idealized processes. It compares those two, and the difference between those two models is used to generate how your plant will react to that data. So again, what you're looking at here is with reactive control, you get more swings in the process. But with this predictive logic, you can maintain closer to an idealized process model for your plant. So you have higher quality of the system. The SCADA data is forming a descriptive analytic model. It's showing how that plant has worked in the past. You can then analyze that data for a diagnostic analytic. A lot of times when we go into plants as SEDAC doing our assessments, we're digging into this data for you, and we're kind of doing these two trends ourselves. Looking at that historical data to figure out how your plant has reacted in the past. Sometimes we can do a little bit of diagnostics on that by looking at, is your DO swinging off set point significantly? Is there a way to optimize that? The nice thing about these predictive controls and AIs is that kind of builds that into your plant process and SCADA system automatically. So it continuously improves the plant and maintains long-term energy efficiency of your systems. Putting those two together into an AI program, a digital twin type system, you now have some kind of predictive analytic. Your plant sees an upset, it can look at historical data and say, okay, this is how it's reacted in the past, this is how it ideally should react, and now it can predict what it needs to do ahead of time and adjust your plant to meet those targets. It can adjust flow rates for your return sludge, for airflow rates to basins to optimize your treatment process. And the nice thing too about AI is you can get into prescriptive analytics, optimizing functions, putting up alerts to the operators and things where they may have to be involved in some of the changes to the process. Maintenance alerts can be automated in this way as well. So there's a lot of depth and detail that we can get into using AI programs. So this is again just an overview of those analytics. The value they can provide to the plant increases as you go from left to right, but their complexity, the cost of installing them also increases as you go left to right. And so finding the best balance for what your plant needs, what you can get to, and what you can afford is the ideal here. just some examples of what we've seen with AI automation and predictive controls. There was a wastewater treatment plant in Cuxhaven that implemented AI controls. They had some virtual sensors. So these are the sensors that are ahead of the plant at the influent level, feeding data into the AI system. What they did as a test is they ran this in parallel with their treatment basins. So they had a couple of basins running on this AI program and a couple operating on their traditional process, and found that with the AI system implemented, they had about a 30% reduction in their energy use. And once they implemented that throughout the whole plant, it was about a 1.1 million kilowatt hour annual reduction in their energy consumption. It also greatly reduced fluctuations in the energy required to treat the process. So they had more stable operation of the plant, and kind of optimize that the metric of energy per kilogram of loading coming into the plant. So just it's a high level overview for feedback control. The advantages are it's generally easier to implement. It can respond to more complex interactions than automated systems, which have a more simplified model. You have fewer sensors required, which reduces your long-term maintenance of keeping those sensors working properly. And you don't need to build that complex model ahead of time. So you're reducing your initial installation costs. The disadvantages, though, is you do have a slower response since you're responding after an upset comes into the plant. There's more potential for upset from large swings. If you've got, again, an industrial client, slug loads coming into the plant, high I&I issues, you have to be, there's more labor involved for the operators than to react to those things, adjust the plant as needed to account for those. And control can be destabilized by poor logic control. We've seen in some plants where the DO never really settles at a set point. It's bouncing back and forth, 1.5 milligrams per liter. Ideally, with an optimal control, that should settle at your set point, less than 0.5 milligram per liter adjustment, unless you've got a really large upset coming into the plant. For feed forward control, you get that predictive response. It's much faster, so you have a more stable process potentially. It can handle large and rapid upsets better than a feedback system. You have better control for more stringent regulatory limits as those are coming down the line. And with proper design, pairing it with feedback control and, or other systems, it can be more stable. However, if it's implemented improperly, it can be less stable. So on that disadvantage side, you do have to put a lot more work on the front end as far as implementing feed forward controls and AI logic. You do have more sensors required in the system. You do need more data input for proper control of the system. So it does increase your maintenance costs long term. And there are limited situations where the control variable has that predictable reaction to the system where you can go with just a feed forward control. Most plants have more variability than that. And so usually there has to be some pairing with a feedback cascade or a larger amount of sensors in order to maintain stability for a feed forward system. So I believe now we'll be transitioning to Zia.
Awesome. Thank you so much, Shawn, for sharing kind of the basics about different control strategies for activated sludge facilities. And I am thrilled to introduce Zia to our call, Zia Qureshi from NORESCO. He has 52 years of experience in over 500 wastewater or projects in wastewater, water, waste management, and other environmental projects. He has a vast amount of knowledge. We had a lot of fun chatting with him in preparation for this webinar. So I'm so glad that he can join us here today. So thank you, Zia, and for joining us, and take it away.
Thank you. Thank you. Good morning to all. And thanks, Cassie and the SEDA organization for inviting me. As Shawn did a tremendous job. I don't need to say anything more. But I'm going to sort of give you a sensitivity to some areas that are easily ignored or overlooked or they seem to bypass the system, and they invariably are quite important to kind of think about. So with the time limitation, I'm going to go pretty quick with my presentation to fit in the allotted time. Some of the slides may have a very small script in there, and I think Cassie will facilitate a copy of the presentation. So with that, the topics, Cassie, next slide, please. That's what I want, is that I'm going to discuss 3 topics. Shawn has done an excellent job in setting me up to discuss the first one, feedback and feed forward. I'm going to discuss SCADA versus DCS, and then I'm going to discuss a very misunderstood concept of using aeration for mixing. And that is important. And then I'll summarize in general my experience. So there is actually no right way or wrong way. Everything works. However, technology is changing rapidly. And I believe as practitioners, we have to open our mind to accommodate the new technologies that are coming into play. So let's look at the first one, the feedback, feed forward. As Shawn indicated, are important considerations for monitoring and achieving treatment. If you don't address those elements, then typically, in my simplistic way of thinking, feedback is reactive, feed forward is proactive. And when you have ammonia loading knowledge up front, it stabilizes the aeration and nutrient removal. And DO is still the dominant parameter. Don't misunderstand that ammonia is going to replace DO, but that's kind of how this system functions. So feedback is essentially, it utilizes and a lot of people don't know, but we talk about PID. What PID is a proportional integral derivative tuning system. And it's an algorithm that is used in the feedback loop. Here is an example that I have on the screen. The limitations of feedback is it uses a nonlinear algorithm. It rarely understands the underlying process, and instability and tuning, as Shawn discussed, are rampant. So you can see at the bottom 2, the unstable DO, the band. And what that means, folks, is that you're wasting energy because you are constantly adjusting back and forth, and it's sort of a catch up or shut down, or catch up and shut down. So it's not necessarily the most optimum. Does it work? Of course it works. But is it expensive and inefficient? Well, maybe. But there may be some practitioners that might challenge that, but that's okay. There are technologies now available that can improve on this. So the factors that make the feedback system not as desirable is the limitation of the PID algorithm. It's not ideally suited for DO control. So I just and this is an example of a Missoula, Montana plant if you see on the bottom, a very dear friend of mine, and he's on this call, Randy Chan, who I think is one of the premier technologists in instrumentation and aeration in the country. So if there is a hard question, Casey, I may ask you to open his mic and he can answer it. So next slide, please. Feed forward. The contrast between the previous slide and this slide, you can see how stable, if you have the ammonia monitoring up front, you could see the stability in the aeration and the DO. It operates within the prescribed bands or the set points. And then you can see in this Denver Metro, and by the way, Toho is a very large utility just next to Orlando. It's in Kissimmee. I think they have about 400,000 customers, if I'm not mistaken, and Denver Metro is a large plant. And you could see the impact of feed-forward controls, how the system is reacting to the effluent characteristics as they're coming in. And this is the key. And if you see on top of that Denver Metro slide, in this particular instance, for 1 MGD, there was a 25% energy reduction. So when I do, and by the way, what Cassie and her team does with Shawn, it's very valuable work, because when I get engaged with a municipal customer, I utilize that package to then develop an architecture around solutions that lead to savings and how to deliver the project through what I do as a business is performance contracting. So energy savings, because as a consequence of forward-looking, feed-forward and ammonia-based aeration is phenomenal, particularly when you have plants that are very significant and tight limitations for effluent characteristics. So these are two examples that I wanted to share with you. The next example is probably, the next slide, please. This is, in my estimation, one of the original ABAC plants that was put in place by Randy and his team at Biochem. And you could see what it did. It provided 45% reduction in energy cost and a 55% better effluent. I should have said it the other way. The nitrogen was reduced. So it was very, very efficient and very reasonable. And on the bottom, the script is very small, but you can see the trends of how the inputs are coming in and how the aeration is reacting and all that. So this is what I think is where the technologists are going. And Shawn correctly said that there are, varying degrees of plants and varying degrees of treatment, but most plants are getting the surprise from the EPA that nutrient removal is coming to their station, and they've got to be ready to address it. And addressing nutrient removal requires a lot of insight and thought. And with that, I think we should go to the next slide. And I'm not going to go through all of these, but Shawn already addressed this feedback, the bioprocess aeration control system. What are the benefits? What are the features? It's precise, accuracy, demand, all that kind of stuff, maximizes blower capacity. And I'll just sort of flip through these and let you guys evaluate them when you get your copy, if you are desirous of a copy from Casey. But that's kind of the summary of the benefits and the features. But here is the next slide is my opinion. And I want to discuss this a little bit with you. Casey, next slide. No, there it is. So here is my opinion. There you go. Leading edge technologists that are on the cutting edge, such as Randy Chan on this call, they look for feed forward because that is really the way things are headed. Whereas the traditionalists will go with the feedback. And I think that owners and operations people should challenge what options do you have and which ones to consider, because it may be true that in some cases the feed forward may not be the ideal setup for you and a feedback is the best way, but then you are operating the plant in an on-off mode and you really don't have any capability to fine tune, and it's always reactionary and reactive. So that in a nutshell is a summary of my actual experience and knowledge in the marketplace of feedback and feed forward. And Shawn did an excellent job on the technical side, so I'm not going to, that's why I sort of jumped over some of those points. But if you have questions, we can answer those. So that summarizes my opinion of feed forward and feedback. And I am a very, very strong proponent of the feed forward, because plant flow pacing, think about the feedback loop, is everything is over designed, everything is operating in a maximum mode, and rarely does a plant operate in peak conditions or peak mode outside of the morning peak or the afternoon peak. So the middle of the day, there's no reason to run copious horsepower of aeration and pumps and recirculation. So that is why it becomes important to have flexibility in monitoring and understanding the pulse of your plant so that you can flow pace it. That's what I call it, based on loadings and flow conditions. SCADA versus DCS. I've had the privilege of being associated with companies that offered 8 SCADA platforms, including the largest platform called Wonderware. And I think SCADA is an excellent tool for gathering information and the status and the condition of the process that it is monitoring. But SCADA has a limitation, in my opinion. That information comes back to a screen, and then you have a human interface. And if the human interface or the individual responsible is not present or is doing something else, there's always a delay and a lag, and it's always sort of hit and miss. So I think SCADA works, and not that it doesn't work, but it has limitations. DCS, whereas, is a much more complicated system, and with the new DCS systems, you can integrate the optimization protocol into the PLCs. So there is no reason for that feed to come back. I mean, it always comes back to a monitor system, but it has the ability to use, as Shawn said, artificial intelligence, or it has the algorithm capability to run internal arguments, so it can correct the excursion or it can optimize a process on a real-time basis. And within the context of IoT, where most electronic equipment and motors are going to be connected to the IoT, I think that SCADA will struggle to match that. DCS will probably get ahead, but it's going to be expensive. DCS is an expensive proposition. So next slide, please. Here is a side-by-side comparison of DCS and SCADA. DCS focuses on central control of processes where it has the ability to optimize. SCADA is a data acquisition, as it says. It has no interpretive or arguments or algorithms that it can utilize. It just reports information. DCS is more sensitive, and if you have an outage, it will have problems. SCADA can endure communication outages. Again, DCS has to be customized, and it has exclusive protocols. SCADA supports open protocols. I'm not so sure about this. I've written this. DCS is a little slower than SCADA, but I think that challenge might not be, that advantage SCADA has will probably go away as processing times are getting faster and so on and so forth. And DCS, in my opinion, is perfect for managing complex systems and optimizing processes. And SCADA is great for keeping track of procedures and processes and gadgets that are part of the package. So in summary, this is a sort of a bird's eye view of the comparison of DCS and SCADA. Next slide, please. So in summary, SCADA delivers important information to the controllers and management, and it can, it then relies on the individual human or whoever it is to manage and fine-tune the data. DCS is a little bit more automatic. It has the ability with artificial intelligence, and if components are not functioning up to, it has the ability to optimize to within reason. So is either one better than the other? They both do the same job. They both can provide meaningful information. DCS is substantially more expensive than SCADA, but SCADA is not cheap. So smaller plants, essentially, if they're wanting to do some sort of monitoring in SCADA, there are cheaper options available on the marketplace outside of the large manufacturing platforms or companies that sell SCADA. And if you want names, I'll be happy to provide them offline. But typically, a SCADA installation is $6+ figures, and it can be in the millions at times. So that is the summary on SCADA and DCS. Next slide, please. Now you're getting into a very interesting topic, and I know Shawn is very much in tune with this, is how many plants there are in this country, and there's a ton of them, where the plant is using blowers and diffusers for aeration. Next slide, please. Will that do the job? So if you're looking for mixing, why aerate? Because some of the new plants that have a tapered pattern of diffusers, mixing becomes very, very important. And so think through what is it that you're trying to achieve and try to minimize the use of blowers and diffusers to do mixing, because alternative options on mixing are much cheaper and somewhat more effective. So I call this blowers for mixing is a technology misapplication. Aeration and mixing, in my opinion, is easily misunderstood. Diffused aeration, as Shawn said in one of his previous presentations, the intent is oxygen transfer, not mixing. Will diffused aeration provide mixing? Yes, of course, but at a high cost. So customizing mixing and aeration solutions are important performance considerations, in my opinion. Next slide, please. So mixing is an important element of aeration, but excessive aeration comes with significant downsides as well. Number one, more energy use, oversizing of blowers, misapplication using air for mixing. It creates operational issues, fouling, plugging, foaming, filamentosis, all issues that operations has to manage, and they result from inaccurate aeration, which results in a high DO or whatever it might be. So in the end, diffused aeration can mix, but it's a very high energy cost. There are other options, and the next slide will give you some, what are I thought it would be important to sort of give you a sense. What is mixing basics? It's used for blending, flocculation, creating a homogeneous liquid, heat transfer. And there are the operational considerations are rapid mixing or continuous mixing. Rapid mixing is also known as flash mixing, and continuous mixing is where you're holding tank contents in suspension, or as the Texans call it, you're rolling the tank. And they become very important in the denitrification, where you don't want to aerate, but you want to maintain homogeneity in the liquid at a desired DO level of 1 and below. So those are kind of the mixing basics that I think about and I look at. Next slide, please. So here are the mixing types, which are low horsepower. You get static mixers, you get high-speed induction mixers, pressurized water jet mixers, turbine and propeller mixers. And I'll give you an example. Just south of me, I live in Houston, and I'm speaking to you from Houston. There was a plant that was using 700 horsepower for aeration, a plant that's only passing through 2.5 MGD. And they literally had about 400 horsepower dedicated to mixing of the tanks. And that was just unreal. And replacing it with a static mixer, they were able to save about 65% on their energy use in the biological reactor. So it becomes very important consideration. Next slide, please. So here's my summary, and I think with the long career I've had, I am entitled to opinion. So my first opinion is there is considerable misunderstanding and misapplication of process control strategies. And I see that across the country. I also see lack of foresight and sophistication in spending time on what is the monitoring, process monitoring strategy. It's often not well thought through. The area that I see, and I'm sure Shawn and his team see at SEDAC, is optimization and efficiency is never a focal point that is given, that is in consideration in plants, and I don't know why. And then the last thing that I observe is, and I hear this from owners all over the place, well, I got an SBR plant when I needed a simple activated sludge plant. So I see a lot of owners receiving their resident designer's process preference. And with that sort of concludes, and I'll go to the next slide for a quick minute to kind of introduce to you what I do. My company does performance contracting, and we focus on energy, of course. So what we do is we take a package that Casey and her team and Shawn puts together for a wastewater facility, and then we figure out a way how we can implement a solution that leverages the savings that we can guarantee. So in a nutshell, that's what we do. And I know the gentleman that's following me, he will take exception to what I'm going to say, but that's okay. We are working on the largest wastewater plant, that is Detroit. I know Chicago is bigger, but the largest peak water plant is Detroit. And we're working on that on the return stream. We just did a biosolids project, an $81 million project for City of Atlanta, which was a belt drying project. We're working on Augusta, Georgia, for a cogeneration biogas project. We're working in Maryland on a cogeneration project. So we're working on very interesting projects and mostly driven by optimization. So with that, I conclude, and I thank you for your time. And if you need any information, I am sure Cassie will facilitate my presentation, and hopefully I have opened some doors. I didn't intend to make you an expert, but I've probably given you some sensitivities to think about.
Awesome. Well, thank you so much, Zia. And yes, I will share the session or the slides after the session. So thank you for that awesome information and for sharing about your experience. So if you have questions, please enter them in the chat. Again, if please hang on with us. Jonathan has an awesome presentation and I am going to introduce him right now. So Jonathan Grabowy joined the Metropolitan Water Reclamation District in 1999 as an assistant structural engineer in the Process Facilities Design Division of the Engineering Department. Since that time, he's worked in various areas, including local sewer permitting, engineering planning, civil design, stormwater management, and capital facility planning. And currently, he's the managing engineer that oversees capital facilities planning, wastewater research, and new technology evaluation programs for the Metropolitan Water Reclamation District. So thank you, Jonathan, for joining us.
Hi, thank you. And to clear something up, Zia, I don't take exception with you making that claim to Detroit. That's perfectly all right with me. I like Detroit's Coney dogs. So I'm going to breeze through a couple of my introductory slides to save some time here. So if you go to the next slide, I wanted to give you a bit of a background on the district. What I'm going to talk about is I'm going to give you a little bit of a background of what we're going to be of the agency. We're going to talk about our resiliency goals, our electricity use, some general aeration information, and some tests and studies that we performed. So the MWRD, or the district, I'll go back and forth between those, was created in 1889 to a response of poor sewage treatment. And we're located in northeastern Illinois. We cover about 92% of the land and 98% of the assessed land valuation in Cook County. We service Chicago and 128 suburbs. We're not a part of the city, but we do include the city of Chicago. We're responsible for regional wastewater and regional stormwater. And we serve an equivalent population of 10.35 million. That's of our last budget. We're in the process of recalculating that number based on the new census information. And that number, I suspect, will be going up quite a bit just based on flows and loads. Next slide, please. So this is just a background. We were created, the original hydrology of the area did not support, was not supportive of as the population grew in Chicago in the late 1800s. So the MWRD at that time was called the Chicago Sanitary District, took some time to re-engineer the hydrology of the area to improve waste treatment. Go on to the next slide. Just diluting the flows was not a sustainable solution. The MWRD moved forward and started implementing treatment technologies. Currently, we have 7 treatment plants located throughout Cook County. And our plants are nearing 100 years old. The Calumet and the Northside Water Reclamation Plant, this is an older slide, it's the O'Brien Water Reclamation Plant, those plants are very close to 100 years old right now. And so that is going to be something that comes up a little bit later in the presentation, the age of the infrastructure. The other thing is the next slide, please. One issue with the older cities is you have a combined system. And our solution to combined, to addressing the combined sewage overflow is that we implemented a tunnel and reservoir plan, otherwise known or affectionately known as deep tunnel. It's a network of large, deep tunnels that are up to 30 feet in diameter, and they go into holding reservoirs that allows the plants to catch up during rain events. This does introduce a lot of operational challenges, and it can cause some issues, especially when it gets cold out, like it is right now. And when we have a huge slug of cold water hitting our treatment plants, it can have process implications. So if we could go to the next slide. The resiliency, what we look at the resiliency at the MWRD, it's been a theme at the district for as long as I've been here, but it's just come more to the forefront because it's moved into our vocabulary more now. It's not being able to snap back to where we were, but it's the ability to reshape and improve. And we could be more resistant to the next set of challenges. And do we ever have the next set of challenges coming our way between between the climate change, between energy costs, between aging infrastructure, and new initiatives coming our way? It is a very difficult and complicated juggling act. Next slide, please. When we look at our resiliency, we look at it basically in 4 areas: our services and function, and are we doing what we were created to do? We are created by an act of state legislature to help the people. Our people, without the people that are dedicated to doing the work here, when I talk about the people, it's the people who actually work for the organization. Without the people, we can't accomplish anything. And the people are key to our resiliency. Our community, we're here to serve the community, and we're here to serve the taxpayers. And the ultimate goal is making sure that we are addressing the community. And the community and the environment are almost in the same, because the community lives in the environment. We need to make sure that we are respecting that and meeting our permits and making the world a better place. One way that we're addressing resiliency is looking at our environmental footprint. And that's through electricity savings. So that's kind of a long segue to get where we're at. So next slide, please. We are really taking a look at our climate, our climate and our footprints. And we do have mitigation goals that are tied. We tied them to the Paris Agreement and part of our strategic planning. So we're looking at a 28% reduction from our 2005 carbon levels by 2025, and an 80% reduction by 2050. Our stretch targets are, we're looking for a 50% reduction by 2025 and a net zero emissions. Next slide, please. This slide, you can see kind of where we are at with our current goals. We're coming really close to our 2025 stretch reductions. As you can see that we met our baseline goal in 2020. We do have a few things. You see a big spike that happened in 2018, 2019. That was some process upsets associated with older infrastructure that is being phased out. And we believe that we are on a sustainable path economically and environmentally to meeting our goals moving forward. So what does all this have to do with aeration? As Zia mentioned, aeration is a huge cost. So if you could go to the next slide, please. It's a huge cost for us. Our 2022 budget is $49 million for electricity. That is a lot of money for electricity. Roughly $22.5 million of that is going to be used for aeration. In 2020, that was about 100,000 metric tons of carbon dioxide equivalents coming from aeration. So that is a significant impact on the environment. And where you're going to make the biggest changes is through making a more efficient aeration process. LED lights are great and all, but building lightings maybe 1%, maybe 2% of our electricity use. The biggest bang for our buck is going to be in aeration and pumping. So if you could go to the next slide, please. As we all know, aeration is a very necessary process in wastewater treatment. It increases oxygen transfer in wastewater. It's essential for the aerobic organisms, and it's very helpful with ammonia removal. I agree with what Zia was saying, is that using aeration for mixing, it may not be the best technology for mixing. However, in absence of other technologies to mix, we need the aeration to mix. And we are working on different ways and strategies to keep our solids in suspension, and we are moving forward on that. Aeration also has secondary uses of scrubbing organics from inorganic grit. We use it as part of our airlift and moving solids through our plants. We found it to be a very efficient way of moving our solids through our plant. And potential savings for aeration are installing DO control and reducing DO, implementing aeration-based, ammonia-based aeration control, Looking forward, currently, right now, all our plants are operating with an old ceramic plate spiral roll configuration. And we're looking to modernize our aeration technology. And another thing that's really new and kind of coming through is granular sludge, both in batch and flow through. I'm not going to talk a lot about that, but we are starting to look at those technologies. They're very interesting. They do have a lot of promise, but they also have a lot of big question marks that need to be we need to take a look at it. If we could take a look at the next slide, please. Some of the barriers with achieving aeration savings, blower turn down capability is huge. If you can't turn down your blowers, you're not going to save electricity. Valves have to be actuated. You can't have manual valves. Some of our areas have hundreds and hundreds of valves, and if they're not actuated and if they're older valves, it will be a big barrier to saving in electricity and aeration. Mixing requirements. We can't have especially with the spiral roll configuration, we cannot allow the solids to settle on the ceramic plates. It will cause clogging and lead to more problems. A big barrier to aeration savings is reliable and robust sensors. Finding sensors, installing them, maintaining them is always a big deal. And we really have to, and that has to be something that has to be really looked at. There can be treatment issues associated with that can be that you can get from trying to implement aeration savings. You can have scum issues floating in your aeration batteries. You can have filament issues. You can have settling on the aeration plates and clogging. You have so you could have bias by some operators, and that could be, and you can losing nitrification. Those are all different things that can be a barrier to achieving aeration savings. But a lot of these are fixable and solvable. And I'll go into that. So we did a couple tests. So if you could go to the next slide. We did an ammonia-based aeration control test at our Stickney plant in 2019. This was based off a process model that showed that we could get about a 32% savings in airflow using ammonia-based aeration control. Stickney has actuated valves, but we have very limited blower turn down. Our blowers are extremely large. We just can't go out and install new blowers with turn down, and getting the controls in there for the blower turn down is not a simple process. It's going to be a challenge to implement savings, but we are looking at it. The blower vane system and controls really turn down, really limit what we can do. So our test was focused on a tank and to a control tank, and whatever we couldn't save was kind of blown out through the other tanks, but we were able to see if the potential for savings was there, and there is a savings there. We looked at a bunch of different methodologies. We looked at feedback directed ammonia control, feed forward ammonia-based aeration control, and feedback cascade ammonia-based aeration control. We selected the feedback cascade method because the nitrification of the DO could be optimized, and it was a simple enough process for us to do internally with internal staff and with our existing resources. If you could go to the next slide. This test was done in 2 phases. We tested a pair of aeration tanks in each of the 4 batteries at different target effluent ammonias to see kind of how well the system would perform and try and identify a range where we would want to hone in on. And then after we completed that phase 1 test, and that lasted about a couple of weeks, we moved to our phase 2 where we tried to optimize a battery. There you go again. You can see in the 0.1, we did have to have a minimum in there for mixing, but we did look at reducing that to make sure we did not have, and we wanted to be comfortable with every step of the way. We focused, and by optimizing the system, we did find that this test was beneficial, and it did merit further work moving forward. So we did this to prove it to ourselves and to see that it could be done. If you could go to the next slide. So the test showed up there is a potential for an air savings of 26 to 28% compared to the existing setup, but limitations are preventing us from realizing any electricity savings. So focusing on implementing ways to get the electricity savings from getting blower turn down and the valving is critical to this being a successful reduction in energy. We did see that there were one problem that we did have with the cascading ABAC control was what Shawn talked about, is that you could see that there was going to be a lag in controls and you could see some ammonia spikes. We did see that, and that is absolutely something that could happen. I saw some people were asking about cost of sensors and stuff like that. Sensors are expensive to maintain. Each ammonia sensor requires weekly checking and 60 hours per year of maintenance per sensor. And if you have 2 sensors per tank and we have eight tanks per battery and we have 4 batteries, that's quite a bit. That adds up really quick for our Stickney plant. The DO sensors, conversely, are a lot less expensive. They're 25 hours a year for annual maintenance and $750 a year in consumables. So you can see that a reliable sensor, even if they are reliable, you have to really stay on them to make sure that you're getting good data and your system's making good decisions with it. We need to make sure that we are releasing our proper DO to our receiving waterway. We have permit limits on DO that goes out to our receiving waterway. So we need to make sure that our affected DO, we're meeting our DO requirements. With the Stickney test, it was very difficult to tell if there were other treatment areas because we were only doing 1/4 of a treatment battery. So it was very difficult to see if there were any other operational difficulties. So if you could go to the next slide, talk about our Hanover Park test. Hanover Park is a much smaller treatment plant. I'll go back. I didn't mention how large Stickney was. Stickney has a daily max flow of 1440 MGD, where Hanover Park, I want to say, is someone's going to tell me I'm wrong. It's about 20, has a 20 MGD of the DMF. So it's still a large plant, but much smaller than the Stickney. Recently, we put a turbo blower in the Hanover Park plant, and it was installed by our trades, and this blower has turned down. The study, we looked at a study to implement a ammonia-based aeration control to see if we could realize any energy savings. We went with a cascading feedback control. We do have plans to go forward and further investigate a feed forward control on this. But we want to walk before we can run on this. And you can see on the chart below, you can see where we had our set points and how we were going about it. One thing is the mixing. We don't have mixers in our tanks. We have to keep our solids in suspension, and we have a ceramic plate spiral roll configuration at that plant. So it's important not to let the solids settle on the plates, or else it will lead to a lot more problems. So if you could go to the next slide. So below you can see some numbers where we compared our control tank to our test tank. Test 6 was our control tank, and tank 8 was our test tank. And the Hanover Park plant is a great research facility. I don't know if they designed it that way, but the really nice thing about it is every tank is basically one treatment train. You have a primary tank, an aeration tank, and a clarifier, and they're all in line. So you have like all these side-by-side treatment trains. So it's really easy to do a comparative study. Sometimes there could be a little bit of an issue with our return flow, which can affect the initial ammonia. So you could see, like on the 21st, you could see a really low influent ammonia as compared to tank 8. But even with the lower influent ammonia and a DO control, you could see that the significant savings was at you could see a significant savings was realized. with this. If you could go to the next slide, please. And the next slide kind of shows a summary. And even though we are dealing with the same treatment plant and side-by-side tanks, you can see before the ammonia-based aeration control, you can see a huge influent ammonia that was a huge air demand that was necessary, and that was due to the DO control, and it was just a different you had different influent ammonias at that time before the control went in. But once the control went in, tank 8, you could see how it significantly reduced our air usage. And then shortly after we completed the test, you could see how we put 6 in the ammonia-based aeration control, and now the whole plant is operating in that mode. We were able to achieve permit compliance for both tanks and the entire plant. We showed a 17% reduction in air to our aeration batteries. One thing that we did notice is that filaments can be an issue. We had summertime filament issues at Hanover Park. Also, another thing about this test, if any of you were in northeastern Illinois in 2020, we had a couple significant factors affecting us. We had a lack of rainfall after May. We had the wettest May, and then it was dry. And so we had very low flows coming to our plants. Also, we had the pandemic going on, and a lot of people were at home, and flows were even lower. So we had a lot of high ammonia problems coming at the plant, and we had a lot of issues going on. We were able, this mode allowed us to meet permit. However, we did have a lot of significant challenges that threw us some curveballs with this. The savings for the plant was looking to be about $33,000 on an electricity expenditure of $438,000. So it's nothing to shake your finger at, and this is ripe for additional study on this. If you could go to the next slide. So the next thing we had an opportunity is that you heard me talk about old infrastructure, spiral roll ceramic plates, and spiral roll ceramic plates. Very difficult to find a lot of places that still have spiral roll ceramic plates. We completed an aeration modeling study for our O'Brien plant as part of our phosphorus feasibility study. As a lot of people have these new phosphorus permits coming in online. We knew that we had to do significant work at our O'Brien treatment plant to facilitate phosphorus removal. And the feasibility study recommended an additional battery. It recommended additional changes to our existing infrastructure. Like I said, O'Brien is one of our older treatment plants. It's nearing 100 years old. And we have old concrete, we have old gates, we have some old methodology in some of these older batteries there, where it's time for some, it's time where we need to really take an opportunity to upgrade it. So when we did our study, we looked at comparing the different technologies that were available to see where we could achieve some savings. We used a GPSX model, and we used sorry, I lost my train of thought. We simulated a dynamic year, and we looked at the yearly energy difference between the different alternatives and estimated a net 20-year present value for a 20-year life on this. If you go to the next slide, please. The results of the study showed that the old spiral technology was twice the cost of what a more modern system would be, which is not surprising at all. There are still things that need to be taken into account, and it is going to be a difficult, and this is only modeled, and this is a paper-based study. There is additional work that needs to be done before I can say, hey, we got to stand behind these numbers, and these are absolutely what it is, and this is the direction that we should be going in. But it gives us an idea of potentially the future. If you could go to the next slide, please. The next steps that we're at, we have the next steps, especially to inform where we're going to be going with our O'Brien is that we have an aeration battery at the Egan, our Egan plant, where we're going to be slated, where we're going to be testing a brand new configuration in plates. We have a full floor aeration system that was installed in 2000. It suffered from a number of treatment issues. We took additional time to take a look and finding ways of improving that system and implementing a more modern full floor aeration system to see if we can get it to perform where we need to. On top of that, we're scheduled to get a turbo blower with turn down at that facility. So we will be better equipped to really do a full scale test of this facility and have a really good understanding of the direction that we need to go district wide. If you go to the last slide. I really want to acknowledge the staff in Monitoring Research Section 129, especially Joe Kozak, Judy Moran, Fenghua Yang, Robert Swanson, and Dan Salabai. And I want to recognize Black and Beach. They did the studies for us at the O'Brien plant. So I know I kind of went through this kind of quickly, but I really want to respect your time. Thank you.
Thank you so much, Jonathan. And your presentation was so interesting. Thank you for sharing those case studies of your different studies and what you're doing around testing aeration at different facilities of different ages and equipment. So it was really fascinating. Thank you so much for presenting, Jonathan. We do have some questions. And so I do want to spend some time actually going into a few of the questions. So we will wrap up around 12:30, 12:35. So get your questions in if you want them answered. But I think the most simple question, Jonathan, for you that came in, or a couple, what kind of ammonia monitoring system do you use at MWRD?
I'm on mute. What we had, let's see, our DO probes were YSI, and I want to say it was HOC is what we were using for, yeah, so we, let's see, I will have to get back to you on that. So I will get that, and it may be different based on the plant.
Okay, that's fine. We can send that out afterwards in a brief notes document. So we'll get that to you. Thanks for asking that question. And also, Jonathan, another question for you. Can you elaborate on operator bias as a treatment barrier?
Absolutely. So you have a person spending their entire career operating a treatment plant, and they've been told this is how the plant's going to be run. You have someone there for 20, 25 years, 30 years running these treatment plants, and we have great operators. All of a sudden, you have someone coming in from the lab saying, "Run it this way." Wait, why should I believe you? I mean, it does take a little bit of time to get some culture change in there to open up to new ideas. And sometimes there's a communication barrier where it comes from, you have someone telling someone to make a change, and they don't take the time to talk to the operator to find out what their concerns are. The operator is hesitant to listen to the person asking to make the change, and you run into issues. Other things that happen that can happen is that there's not enough testing, or there's not enough monitoring points put in that can lead to not enough information going to the operator to really feel comfortable with changes put in. So operator bias, I should have phrased it differently in the presentation. It has to be increased communication with operators. The designers really need to take time out of their day to travel, talk to the treatment plant operators, to talk to the OEs, to talk to the plant managers, to really understand their concerns and be able to communicate it, because that is a big that could be a big barrier when it comes to implementing new strategies. But that's always something when you're putting in a new technology that can be a real problem.
Definitely. Well, thank you. That was such a good explanation, Jonathan. I appreciate it. Zia, do you have anything to add on that question?
Well, I think Jonathan was right on. The disconnect between the designer and the operator is a big issue. And the designer takes the position that you are an operator, you don't understand engineering. I'm the PE and I understand engineering, so you do what I am going to give you. And oftentimes that doesn't work. And there is not a single plant in this country where the design engineer has had a bad project which doesn't function. And so there is a level of mistrust. And I can share with you, I did a project in Luling, Texas, where the day after I installed the controls, I went back and the operator pulled all the controls out and says, I'm going to run it my way, forget your way, you know. And so all of that effort was lost. I think it's changing with the training and the certifications that all states have for operators. That is going to, the dynamics will change. And I would like to hear Jonathan's point of view on this, is that, Cassie, the biggest mystery or the biggest surprise that owners will have coming to their various facility is lack of operating help, because the technology is getting so sophisticated that if you don't have adequate training and education for the operators, these plants are becoming very, very complex.
Yeah, definitely. Have you run into that at all, Jonathan?
Well, that is the complexity of the equipment is definitely increasing, and it does introduce a whole level of complexity. And the other rub on this thing is being a public agency. Things have to go up for public bid, and it gets complicated writing specs. You have some manufacturers that are they produce a substandard product, but they're able to get it in under the open bid, and it can really wreak havoc on you when you have to go with when you have to go with a specified, you're not specifying an off brand, but you end up with an off brand, and that can really lead to a lot of issues. Well, Sia was talking, it made me realize how we did overcome some of this operator bias. And I really want to point out, Fenghua Yang and Robert Swanson. Fenghua did the she did the Stickney study, and Robert did the Hanover Park study. They made it a point to actively communicate with our operators on a very frequent and continual basis to build a rapport with them. And that was one way that we overcame a lot of these bias issues. So it's all about the communications. And Sia, you're absolutely right. Is a lot of times the engineer comes in, sometimes they don't even come on the site. And it's important that they go on the site and they walk through with them and they work with them as they're putting in a new system and work side by side and listen to the feedback that's given during the specific critical design milestones.
Well, the interesting piece, and I think I align very much with Cassie and Shawn, because we are developing concepts and information that leads to solutions as to an engineering perspective. I think that's the difference. Now, Jonathan, I can really help you with your issue of non-favored vendor, because we are already under contract to your division with us. You don't have to worry about the low bid. You select the best technology.
Okay, we'll talk. We'll definitely have to talk.
Yeah, we'll talk offline about that one. We do have a couple other questions here. We have a couple of series of questions. AI during rain events, maintenance replacement of sensor costs, and ammonia diurnal peaks. So I think if you could answer any one of those to wrap up our session today, that would be helpful. And then I will send, we got another question in here too, and I'll send that to both of you for some responses. But I guess AI during rain events, maintenance replacement of sensor costs, or ammonia diurnal peaks. If each of you want to take one of those, that would be great. Don't jump in at once.
I
no.
think Shawn is equipped to go with the AI.
Yeah, we're just dipping our toe in the water. Another plug here for Fenghua Yang. She's heading up this AI committee with WEF, and she's really pushing for AI to move forward at the organization. She's doing some really wonderful work. We are planning on moving forward with AI. We haven't had a lot of experience with it. We've tested it in a virtual setting, but I really can't comment on how that could be done. But the question on using feed forward control to predict ammonia or phosphorus concentrations in the aeration tanks, that goes to I think that goes to sensor technology. You have to know what's coming into your plant.
Real quickly, I do have to leave for another meeting here, but I did want to address how AI can address diurnal flows and changes, things like that. As I touched on in my presentation, one of the types of technology is that digital twin technology, where you're building a baseline from historical data. So if you've had past ionized swings or ammonia swings, you've got a record in your SCADA data, hopefully, if you've got good SCADA tracking, of how your plant needed to react to that. And so you can build in the AI system an idealized model of what that reaction process should be. And then AI has a capability to learn over time if those initial changes that were in your historical trends don't have an optimal end result, then it can tweak kind of the process procedures and things, the set points in the system to adjust for future events. You get a better response over time.
Great, thank you, Shawn.
I do have to step off, so.
Okay, well, I think that we can, go ahead, Zia.
Can I make one comment? And I think this Jonathan will agree with me. What we discussed here and all these options and all, it has limitations. And size is one limitation, such as the Stickney plant or the Detroit plant or the Washington suburban plant in Washington, D.C. The infrastructure is set up for gargantuan machines. And to retrofit and change them, there is, when you have a 4,000 or a 10,000 horsepower blower, there is nothing available than what they're using to replace it with. So there are those technology limitations at the massive scale of some of these plants. So let's not cast an impression that there is all these solutions fit everywhere. They have limitations.
Definitely.
You're absolutely right. A 10,000 horsepower blower is a sight to be seen. It's the equivalent of 3 locomotives. I mean, that's how much horsepower it has, and it is really something to see that thing fire up. And we have 4 of them at our Stickney plant.
Wow, that's incredible. Well, thank you so much for your questions today. Thank you to all of the folks that stayed on the line as well. I'm going to work with IEPA to squeeze out another half CEU for you for sticking on the line with us. So thank you so much. Thank you to Zia, Qureshi, and also Jonathan. Thank you so much for presenting today. Thank you for being willing to stick on a little bit more or longer than expected and answering some questions. I will send you a couple questions that we didn't get to answer today to gain your responses, but we truly appreciate your time and what information you had to share. I think that this was a fantastic webinar. So thank you so much for making it so special. So just as a wrap up, thank you. So just to wrap up, this webinar has been recorded and I will send it out either later today or tomorrow to all attendees. Once we get that CEU number, course number from the Illinois EPA, I will send out the course number and all the certificates to everybody who participated. So thank you so much. Please feel free. I will send our contact information of our presenters. Feel free to reach out to them if you have any questions. And again, we hope to see you on our next webinar series. I will keep in touch with everybody about our upcoming events. Thank you so much for your time and have a wonderful afternoon. Take care, everybody.
Thank you. Thank you. You too. Bye.
Thank you.